Continuing our discussions about trigonometry, we are now going to begin to define our trigonometric functions. The first thing that we need to make sure of is that we recognize that for all of our triangles that we will be working with, they will be right triangles. And a right triangle is simply a triangle that does contain a right angle or 90-degree angle. We will also be very consistent with how we're labeling our triangles. So for labeling our triangles, our angles will always be labeled with uppercase letters, and our corresponding sides will be labeled with lowercase letters. And so for our angles, again, uppercase letters, and sides are lowercase letters. We are going to be identifying the relationships between our sides and angles, and we will do so by first establishing the law of similar triangles. So, definition of law of similar triangles. Two triangles are said to be similar. Notice similar, not same, if their corresponding angles are congruent or equal, and the corresponding sides are in proportion. In other words, similar triangles are the same shape, but not necessarily the same size. So let's look at this big triangle we have right here. So the first thing that we are going to identify is the fact that this is a right triangle. So this triangle has an angle that is at 90 degrees. Now this big triangle, I'm going to call it angle A at top, angle B to the side, and our right angle we're going to call angle C. So this is triangle ABC. Now angle A, as we can see, is capital A, and its corresponding side is opposite it, so this is side A. Angle B has corresponding side B, and angle C has corresponding side little c, which is the hypotenuse. Now notice I have another triangle drawn inside my triangle ABC. Now obviously this is not the same triangle because it is so much smaller. It is a smaller triangle, but it is meeting the definition of a similar triangle because it has the same shape, but it is not the same size. So I have pulled that triangle to the right, and because it's a different size but the same shape, we're going to notice that I can't call it triangle ABC. Instead, I'm going to call it triangle DEF. Now notice, originally they shared angle B, didn't they? So that means angle B has to equal angle E. Notice both C and F are both 90 degrees, so that means angle C has to equal angle F. And by process of elimination, since all triangles add to be 180 degrees, that means angle A has to equal angle D. Therefore, these are similar triangles. And so, by the definition, they have to have proportional sides. Now, what does that mean? That means I can take any side of triangle ABC, such as side A, and I can choose to compare it to another side of triangle ABC, such as side B, and that will be the same. And let's write down our sides. So for triangle DEF, it has lower leg D, height E, and hypotenuse F. So from triangle ABC, if I compare side A to side B, that would be the same as comparing side D to which side? And that is side E. Now, the whole point of law of similar triangles is to help us understand it's all about how the ratios are being set up. It's all about how the sides of our right triangles are being compared to each other. And so this leads us into the definition of our trigonometric functions of acute angles. So our 6 trigonometric functions are sine, cosine, tangent, cosecant, secant, and cotangent. And the definition of sine of any angle is always opposite compared to hypotenuse. Now notice, opposite is in the numerator and hypotenuse is in the denominator, but if we were to reciprocate that, that gives us hypotenuse divided by opposite, which tells us that sine and cosecant are reciprocal trigonometric functions of each other. Now for cosine, cosine of any angle always looks at adjacent divided by hypotenuse, which means secant and cosecant, secant and cosine are reciprocal trigonometric functions. And then tan of any angle always looks at the opposite side compared to the adjacent. And so cotan looks at adjacent compared to opposite. So tangent and cotangent are reciprocal trigonometric functions. Now notice, every time we look at a trigonometric function, it is always of an angle. And so in relation to our angle, we have the opposite side, the adjacent side, and the hypotenuse. Hypotenuse is not in relation to any angle. It is the longest side. It is the side opposite our 90-degree angle. So we don't talk about it in terms of relationship to our angle of interest, theta. It is just the hypotenuse. So an example of a Pythagorean identity is a 3, 4, 5, where the opposite side is 3, the adjacent side is 4, and the hypotenuse is 5. And we can verify that this meets a Pythagorean theorem, the Pythagorean theorem, because 3 squared is 9, 4 squared is 16, 5 squared is 25, and 25 equals 25. So this is just one example of a Pythagorean triple. So also of note is when we go to set up our ratios, they always need to be simplified and rationalized. We'll talk about that in a moment. So for our first example, we have right triangle ABC, where A is 5, B is 7, and C is 74. Now C is 90 degrees. It's a right triangle. So that means side A is 5, side B is 7, and our hypotenuse is the square root of 74. And I'm going to do the same thing that I just did up above. I'm going to verify that. So using the Pythagorean theorem, 5 squared plus 7 squared is supposed to equal the square root of 74 squared. We have 25 plus 49, and the square root of 74 squared, the root and the square cancel and give us 74. And notice 25 plus 49 is indeed 74. So this shows that this is indeed a right triangle. Now I want you to be very careful. For question number 2, it asks us to determine each ratio. So for our first one, our angle of interest is angle A. Now remember, sine of any angle always looks at the ratio of the opposite side compared to the hypotenuse. And in this case, because our focus is angle A, the side opposite angle A is side A, and that is 5. And the hypotenuse is the square root of 74. But remember, we need to rationalize this. So we need to multiply by the square root of 74 over the square root of 74. And this gives us 5 times the square root of 74 over 74. Now cosecant is the reciprocal of sine by definition. So if sine of A is equal to 5 over the square root of 74, then I'm going to reciprocate that to get the cosecant of A. So this is equal to the square root of 74 over 5. Now notice that I did not use the rationalized version of the sine of A, because in order to get cosecant of A, I needed to reciprocate it. So I wanted my radical to be in the denominator so that when I reciprocate it, it is in the numerator. And this is our final version for cosecant of A. Now tan of, this time we're looking at B. Tan of any angle looks at the ratio of the opposite side as it compares to the adjacent side. So tan of B, this time our focus is on angle B, and the side opposite angle B is side B, and that is 7. And the side adjacent or next to angle B is side A, which is 5. Now you have 4 questions, and we're using the same triangle. So for right triangle ABC, where side A is 5, side B is 7, and the hypotenuse C is the square root of 7, you're asked to determine each ratio. You're going to make sure each answer is simplified and rationalized. And you're going to need to concentrate on your angle of reference. So for example, the first one is to determine cosine of B. And remember, cosine looks at the adjacent side as it compares to the hypotenuse. Next is to determine secant of B. And remember, secant is the reciprocal of cosine. And we're still focusing on angle B. Our third question is to determine cotan of A. Notice we're looking at A. Now cotan is the reciprocal of tan. Cotan of an angle also looks at the adjacent side as it compares to the opposite side because it's the reciprocal of tan. And for problem 4, now you're looking at cotan of angle B. So your reference has now changed, but we're still looking at the adjacent side as compared to the opposite side. But again, this is in reference to angle B.